yesterday we talked about basic principles of electron microscope, how contrast arises in the microscope, okay, and then what all things which we have to, factors which we have to know to say that we have fully characterized the dislocation, correct? Then we know that especially in materials which contain low stacking fault energy, these dislocations can split into partials, okay, and they can create a planar fault, which is a stacking fault, okay. And I also mentioned that when you look at a contrast, okay, finally we are observing whether a defect is present or not just by looking at what the contrast variation is. Quite often, different types of defects can give rise to similar type of a contrast in the microscope, okay. So unless we understand how the contrast arises, and when we do microscopy, we get all the parameters, the different G vectors which we use, so that microscopy gives some micrograph which gives some variation in contrast or diffraction. Then to get some meaningful information out of it is how we analyze the results, taking some models of the crystal structure. That's what essentially gives us that information about, okay, the sample, correct? So that's what essentially we have to do it. And I said that, and yesterday we covered information about strain field around, strain field in the material, correct? How to image strain field. Today I will cover a little bit of that, that will come later. But essentially, another type of defects which can be there is which are planar defects, okay? That's what we will consider today. What all types of planar defects we can have? Stacking fault is one, okay? Antiphase boundaries in ordered materials are planar defects. Then we can have Moiré fringe contrast comes in from interfaces between different phases. Then domain boundaries, thin precipitates, all of them give rise to, all of them are essentially planar defects, okay? And what sort of defects are these? Defects generally don't introduce much strain in the lattice. Essentially, it is a displacement of the lattices one with respect to other. They also give rise to some contrast in the material. How we analyze or how we get information from looking at the microstructure is what will be the subject of today's talk. Okay. When we look at the contrast from material, this yesterday I had explained how the contrast comes, because it all depends upon the term G dot RD, correct? And this equation you are familiar with it. That is the amplitude of the electron wave as it passes through the sample, and at the back of it when it comes out, how the amplitude changes. It depends upon, okay, the deviation from the Bragg condition, as well as if a defect is there, what is going to be the G dot, that is a Burgess vector which we, not Burgess vector, the diffraction vector which we use to image the defect, okay, the dot product of it with the or the defect vector, okay. This, okay, and this part of it for a perfect crystal, how it will look like, the dynamical theory, all these aspects of it I had explained yesterday, so I am not going into it again. Okay. A planar defect is what it is, that we can consider the sample. Here what I have done is essentially, ideally this is one part of that sample, this is another part of the sample. If you look at these two, yeah, thank you. What have I done? It's essentially this part is slightly displaced with the other part, correct? This is a sort of a defect which it can occur. This defect could be either parallel to a foil or it could be inclined. That's what essentially all types of planar defects are going to be. What will be the effect on the amplitude of the wave. That's what essentially has to be calculated. Okay. This expression which I had already explained. Okay. So in this, what is essentially important is that this term exponential 2 pi I s dot z, this is corresponding to if a deviation from the Bragg condition, how it's going to affect the intensity. This is what is defined as alpha 2 pi g dot rd. Whether this factor becomes 0 or non-zero, that decides the extra contrast which is going to come in the image, correct? What is essentially important is that if a defect is present at some up to particular thickness T1, if you take that from here to here to T1, then this is like a normal sample. Then the expression is that there is no defect present. So this term alpha will be 0 in the expression. Then plus this side, when you can, there's an extra phase factor which has been introduced into it. Okay. That's what. So the total amplitude now is going to change for the beam which is going to come. This is how a contrast comes as far as the dislocations are concerned. There's a way in which this could be represented also when we have this sort of small phase differences are introduced. We know that in a vector, we can just do a vector algebra A plus B, or if we represent them in a phasor diagram also, amplitude and the phase. This you might have studied, right? For a coherent wave, you can do that. So that is what essentially is being done in many of these calculations. Okay. I will not go into detail, but essentially, if you assume that it is the alpha equals 0, then what is essentially is going to happen is that as the beam passes through this sample, okay, there is going to be some scattering. Okay, the amplitude gets reduced, and this is what essentially the phasor diagram represents with respect to it. It comes back to 0 at the end of it. So we find that the defect is not being seen. If a defect is being introduced into it, what does this say from here? If I plot from here to here, it is like many waves which are there, each making a small angle. The net amplitude and the angle at which the phase of this wave function occurs, that's what that information which we get from this. This also could be used to find out the amplitude, and amplitude we know the size I star, if we take it, we will get the intensity. Okay. This is what the calculation is about. Okay. But what is essentially important is that you can forget about it for some time, but you should know that when you have to quantify it, this is the way we theoretically generate the amplitude of the wave at different points when a planar defect is present. The same way it could be done for dislocation as well. Okay. On this basis, we can consider here a crystal with two different lattice parameters. You look at it here, it's a two-dimensional, I shown just one-dimensional one. Here if you see that this is the lattice parameter, here it's a lattice parameter is slightly different. So they are joined together, correct? When the beam enters from here, then you find that some phase differences will be introduced. Because of this phase difference, what is essentially going to happen is that when you know that waves with two different frequencies, it's equivalent to two wavelengths if you choose. Here also, this will have a wavelength λ1, this will be having another wavelength, right? The periodicity, if you look at it. When these two are there, they will give rise to a beat frequency. Like sound, we have studied that beats, na? There's two frequencies, and then that they together, when they mix it, we will have a frequency at which it will be occurring, which will be having a different frequency at which it will be. That is exactly what it is going to be there. Here also the fringes will occur at some periodicity which it can be seen. Okay. It is much higher than that of the lattice parameter of either phases. Because lattice parameter is what decides the periodicity in that particular direction, correct? So our D spacing will define periodicity, any specific particular direction we look at the lattice, right? So essentially, the fringes could be rotational Moiré fringes, or it could be a translational Moiré fringes. Okay. How this will appear in the microscope is essentially, if you look at the diffraction spot, this is one spot. Okay. Then due to a lattice with a particular lattice parameter, it will give rise to a diffraction spot at one particular point. Lattice due to the another diffraction, the lattice parameter, which is just below it, it will give a diffraction pattern at another distance. If you put an aperture around this one, covering both of them, if we take it, in the image, both these fringes corresponding to both of them will interfere and give an interference pattern. I don't know whether you have seen this. If you go to any science and technology museum in the country, you will be able to see this sort of thing. If you have a jolly one type and you put another on top of it, you rotate it, what you see as that image is not same of the individual ones, you don't see it, something which is a beat which you will be able to see it. This is exactly what it is going to be. It's as simple as that. Okay. So this is what essentially a diffraction pattern which comes when there are two lattices, one sitting on top of the other. So you can see that from here, this is one diffraction pattern corresponding to it. This is another diffraction pattern corresponding to it. There are some extra spots come because of some other consideration which I am not going into. Okay. This will give rise to a sort of a fringe pattern which you can see. With this pattern, what has been seen even before that the dislocations were actually imaged, one could see like here if you see it, these sort of places. You look like that we draw the dislocation image, na? This could be obtained. This is because if you have one lattice which is where a defect is there and another lattice comes on that other side which is perfect lattice, then there is some lattice parameter differences are there. The beat frequency will give rise to this sort of an image pattern, with which also it looks like the way we draw in a book, how the dislocation looks like. Okay. This I will just leave it. Okay. Now I will come back to that's one type of a fault. And another type of a fault which we consider, there is a stacking sequence, there is a variation is there. So the stacking sequence variation can give rise to variation. In fact, it can give rise to some new phase. Locally, a nuclei of a new phase also can come, because in FCC you know that if you generate a stacking fault, that is nothing but a nuclei of a HCP phase there, correct? So what I have done is shown stacking sequence along. What I had shown is these directions where close-packed planes are there, and putting atoms on top of it, we can generate an FCC lattice, correct? That is, you consider an FCC unit cell. Okay. On 001 plane, keeping one plane on top of the other, we can generate. Okay. And if you consider that the stacking sequence on two directions, 110 or 001 direction, the stacking sequence will be AB, AB. Okay. What I would like you to work out is that in this stacking sequence, if we look at it, will a stacking fault be generated in FCC? Okay. You create a fault by moving from one A position to B position in one layer. Just work it out as an assignment. Okay. Then you will understand. Okay. Normally, the way we can consider this FCC structure also is stacking along 111 direction. In 111 direction, if we consider it, okay, the atom on the next plane which is sitting here, there are a few options that it can move from here to here, or move from here to here, or move from here to here. Okay, all the three options are there. All the three will move it to a position, either this position which is identical. Okay, that's what we are trying to look at it. Okay, so that if it moves it, then that gives rise to a stacking fault. Okay, these are called as intrinsic stacking faults. Okay. Why they generate a stacking fault essentially is because in any layer in a close packed 111, we have two positions. An atom can sit in this position or in this position, both are thermodynamically equally favorable. It's only a choice which it decides. That choice which it takes, it is whether it forms or not depends upon the surface energy of the new surface which is created. That's what we call it as a stacking fault energy. If that energy is low, the probability of this occurrence is high, because in fact stacking fault energy also can be considered as a representation of the fault probability. We can look at it. Which one? No, when the stacking fault is created, what is the energy difference? Because when it can go to B or C side, where is the difference which is coming? Both the sides could be equally probable, it can occupy. A layer, or once an A layer has been there with atoms at this position, the next atom sits here or in this position, thermodynamically it is equally probable, okay? And when the third layer comes, that will be coming on the next layer, A, B, C, the stacking sequence which it goes, every layer is like this. If one of the layer interchanges the position, but as far as that layer is concerned with respect to A layer, this atom could sit here and this atom could change. Why that is not possible? Because even though both the positions are possible, the same atom cannot occupy simultaneously these two positions. If it occupies this position, it has to go to the same layer. That's not possible. That's the way it happens. But the probability, if you look at it thermodynamically, it has a choice to choose. But once that choice has been chosen and the stacking sequence is created, if you look at it, with respect to it, this layer itself can be considered as a nuclei of another phase, right? When you consider the nuclei of another phase, there is an interface which is created. That interface has to be created. That interface comes because of the stacking sequence, okay? That is what, when we calculate as the energy separation between them, is essentially the interface energy. Yeah. Which one? Both are close packed. What it will decide is that we are looking at only from a one layer part of it, right? But the energy which you have to consider it is other than that, that chemical energy, volume energy has to be considered, transformation energy of the bond energy which has to be considered, that we are not putting into that picture. That's what it will make all the difference to it. So when we consider a nuclei, we have many terms are going to be there, correct? Nuclear energy term, strain energy term, and the surface energy term, okay? Correct? Thermodynamically when you look at it. So that's what essentially as a function of temperature, if it changes, when you try to plot for both of them, where they intersect, that is where close to those compositions where you can have either of these phases which is possible, right? Free energy curves, correct? It's clear? Okay. Now, essentially because of this, a stacking fault is created in the sample. Okay. Similarly, in the ABC stacking, as Marc Fivel has explained yesterday, by removal of a layer, also a stacking fault could be created. So there also, if you look at it, if you look at the stacking fault sequence, they remain the same in either case. Whether it is by displacement of atom from one position to another on the stacking sequence, or by removal of a layer or an adding a layer, they create generally a same type of a stacking sequence which is happening. Okay. Only difference between these two is that if you look at the dislocations which are there at the end, here the dislocation will have a Burgess vector, or which will be that B will be 1/3 111 type. In the other case, B will be 1/6 112 type. In fact, that is the way we can differentiate between whether these are a Frank fault or a shear fault, by finding out the dislocations. So by analyzing the dislocations, we can differentiate between these two, okay? And you know that Frank has already explained how a stacking fault ribbon could be generated by a perfect dislocation splitting into partial, okay? What I have written is, if you want, you can work out This is a dissociation which I have written for one particular one. Another one you can do. When you do that for another one, you will understand it much better, these faults. Okay. Now let us come back to imaging of this. So essentially what I had given is just summarize what Marc Fivel has said yesterday about the different types of faults which it can form. Okay. And now this is a tin foil in which there is a fault which is lying. And then we have to define a fault vector, correct? What is a fault vector? Essentially is that when we consider the stacking sequence, one layer is there, second layer, third layer, fourth layer comes on top of it. So essentially 3 layers are there. If we are removing one layer, that will be the fault vector. That is why the fault vector is always defined here as R will be equal to 1 by 3, 1, 1, 1. For as far as the stacking faults are considered. So it doesn't matter whether it's a frank fault or whether it's a shear fault. For the fault, this is always going to be the fault vector that you should keep it in mind. Whereas if it's a frank fault, the dislocation which bounds the fault is going to be with B equals 1 by 3, 1, 1, 1. Where if it's a shear fault, it will be 1 by 6, 1, 1, 2. This is clear? So this is the distinction. So now we are considering it's only the fault which we are looking at it. Okay. We assume that the fault is going across it, which is inclined. Then one can try to calculate with respect to this thickness. At every point, if you see it, if you take a beam which is entering from here to here, it is the fault it doesn't see. From here to here, the fault introduces a phase shift, correct? That's going to happen. And if you do that calculation, this is how the formula will turn out for the intensity. This as a function of T if we try to do it, okay. This factor, S T dash as T changes, this value will decide whether this function is going to variable, whether it becomes 0 or a value which is maximum. This is what it's going to give rise to a fringe contrast. This is how a fringe contrast comes for almost all faults. So if it is an antiphase boundary, this fault vector may be different. That's the only difference is that, but essentially this is how the fringe contrast appears in the microscope. Because yesterday I mentioned about that one sine term which comes, whether it's a sine term or a cos term, depending upon what that angle is, depending upon that, as a thickness if it changes, as we move away from it, there is a variation in contrast, periodic variation. That's what the fringe contrast is, okay. So essentially here also, now when a stacking fault is there, the condition for whether that alpha is there is G dot R should be equal to, if it is 0, okay, or 2 pi, then the fault will not be seen, correct. If it is any other value, we will be able to see the fringe contrast, the fault will be visible. That is the philosophy under which the whole analysis of all the planar faults are carried out in the microscope. Okay. And as I mentioned, to understand this visibility or invisibility criterion, like for dislocations, we have to image them under 2 beam conditions with many reflections. That's what essentially, this part of it I had explained yesterday how it's to be done. Exactly that is done. When that is done for a stacking fault, these are all some pictures of stacking fault which are taken from the same fault, imaged under different conditions. Okay. This is imaged with 200 reflection. Okay. The aim is to find out what is the fault vector. Okay. If you look here, you can see a fringe contrast which could be visible in both these faults. This is a dark field which is taken, where you see that the fringe contrast is changing from top and the bottom. Looking at the fringe contrast, there are some rules which are there, which those who are interested in the books which are there, I will suggest the book at the end of it, with which you can learn these procedures which you have to follow, with which you can identify whether which is the top, which is the bottom, and also one can identify whether it's an extrinsic fault or an intrinsic stacking fault. All this information could be obtained by this analysis. But what is important here is that when I image this with 1 bar 1 reflection, Now you see that this fault is invisible, correct? Only this fault is visible. Now when I image with, actually this reflection is wrong, it is with the 202 bar, if I use this, now you find that both the faults are invisible, okay? Now using this G dot, if for 2 reflections if I get it, we can find out what the fault vector is. That is how the fault vector is determined. Is it clear? But you have to take a pictures where the fault is visible, and especially the condition under which the fault is invisible, which has to be used to find out what is the fault vector. Invisible as a criterion to do it. But there are some cases where you have to use visible one also, which I mentioned for some stacking, not stacking fault, but with respect to partials which are bounding them, where the visibility criterion in ordered alloys, you have to do that. Eh? No, G is the vector, diffraction vector. That is like we have taken a diffraction pattern, right? If I index this is a 110 type of pattern, this will be 0, 0, 0, this will be 2, 0, 0, this will be 2, 2, 0 type of reflection. So this is called as, if I take a 2 beam condition with this one, then this is called as the G vector, okay? That means that the sample has been tilted in such a condition that only 200 planes are strongly diffracting. Okay. So whatever the contrast appears in the image is due to diffraction taking place from 200 direction. So even if with a bright field we take it, so we call it as, this is what the vector which is responsible for the contrast. That's what it means. Okay. So this way we can identify what the fault vector is. These are all some calculations which are being done, which you can do to find out how the fault vectors will look like, because there are many other ways. I said that there are so many other type of faults. Planar faults also will give rise to a fringe contrast. There are some conditions where if there's an overlapping 2 faults are there, one on top of the other. But the fringe contrast from which it may be very difficult to identify which one is there. So in those conditions, simulations are very much necessary. Okay. So this is one which I have taken is, it's a nickel based superalloy which contains fine precipitates where the stacking fault energy of the material as well as the precipitate is low. And when the dislocations pass through the sample, it has one partial could be seen, then the fringe could be seen, the other partials are not visible. With different conditions, when I try to image, different faults could be seen. For this particular reflection, which is 1 bar, 1 bar when I image it, okay, you can immediately see here that the fringes are seen, but the faults are, the partials which are bounding the faults have become invisible. Because here if you see that, you can see a strong black line at the end of it, right? Here you don't see a black line, you see only the fringe which is in between. So under different imaging conditions, stacking fault, in some conditions only the fringe will be visible, the dislocations could become invisible. Under some conditions, fringe and one partial could be visible. Some conditions, the other partial and the fringe could be visible. Some condition, both the partials and the fringe could be visible. There are some conditions where the partials are visible. That's the one which I had yesterday shown for analysis of the dislocation, that is using computer simulation, where the fault has become completely invisible, correct? So all these possibilities are there. Okay. Why I wanted to show it is that in material, sometimes what can happen is that if only the dislocations are visible, the partials is invisible. Under those conditions, one can think that it's a pair of dislocation which has passed through it and creating, shearing the particle. That sort of conclusion one should not arrive at, because one has to image under different conditions to see and identify what the bias vector of the dislocations and the faults which you see. That's very much necessary. This is also another big beam condition, the dislocations are being imaged. Okay. This I had just shown. This is one where you see here, you see some fringe contrast here, And then there are regions where no fringe contrast, there is a weak fringe contrast. What essentially happens is that one layer of fault is there, then the next layer when the fault comes, okay, then also a fringe is going to be there. When the third layer, if you put again a fault, the same fault if I create it, ABC if I move it all, now it has become like a normal stacking sequence. So if 3 faults are overlapping, then that region appears as a normal region. So this is what essentially is happening in these regions. Overlapping 3 faults. There are some regions there are 1 fault is there, some regions there are 2 faults are there. Here again you can see that in this one you can see the dislocation which is bounding them. Here you can see one, the other side you don't see the dislocation, that's what I mentioned. All these things one has to do a careful analysis to characterize these images. Okay, this is one where in some low symmetry alloy, the stacking faults have to be simulated to find out what the fault vectors are. Okay. This I had mentioned what all information which is required yesterday to do that. That's what we require, the G vector we require, okay, the line direction which we require, okay, the foil normal which we should know, that psi g, the extinction distance which we should know, thickness of the foil we should know. Okay. Now we'll come to the other type of a fault which can occur is antiphase boundaries. Okay. In a disordered alloy, okay, if ordering takes place, okay, you assume that the ordered lattice is a supercell on that disordered lattice. Then what can happen is that there are 2 possibilities which exist. Is that when we do an aging, okay, what is essentially going to happen is that 2 nuclei of the ordered lattice form independently. That's how a nucleation takes place, right, when you do an aging. And if it's a stoichiometric composition, it goes into a complete ordered phase. Okay, this nuclei will grow and they will come and join. Okay. In this particular case, the way they have grown, when they join together, that becomes as a single one. You don't see any defect. Okay. And in this particular case, you find that you have when they join together, there is a fault, there is a shift which is going to be there. This shift is essentially, if you look at the periodic conditions, a shift of pi. That's why it's called the antiphase boundaries or pi boundaries. These are all the names which are used because of this shift. So you understand that. So this sort of boundary also is a shift which is going to be there, because of which, if it is inclined, it will give rise to a fringe contrast. Okay, here what I have done is some of the things, the definitions are given, but I had given some exercise which you can work it out later to identify it. Yeah. Which one? Yeah. Yeah, stacking fault also, the part, it's the same, that doesn't matter. So, essentially, if you look here, this is essentially a ordered phase, okay, and this is a body-centered tetragonal lattice. The projection of it, if you view it from the 100 direction, is being shown here. And from here to here, if you go from here and here, if you look at the directions remain that same. But if you put a fix a coordinate system here, now you find that the lattice is slightly shifted by a vector. This vector is called it as the antiphase boundary vector. That you can see that there are various ways in which it can form in this particular system. There are 3 types of antiphase boundaries which it can come in this particular system. Okay. So this sort of antiphase boundary finally gives rise to a contrast when you imagine TEM is a fringe contrast. So if you see a fringe contrast, now you do not know which is giving rise to a fringe contrast, for which unless we try to find out what all the G vectors with which we are doing it, we should have an idea of what the lattice is Okay, this gallium arsenide, this is also going to be an FCC structure. So this will be visible under some conditions, which is here it will be half 110 type will be the antiphase boundary vector. Depending upon that, for some reflections only it will become absent. On that basis we can decide. And there are some another fine structures are also there. In the bright field and dark field, if you take the image, in stacking fault we find that one is asymmetric, the fringe contrast, another is symmetric. Here both are symmetric, either bright or dark in both of them. If you look at it, the first fringe and the last fringe are the same here. Here also, that's a bright, and in the one it's dark. So this is what the difference between antiphase boundaries and stacking fault. Okay. This is just a picture where when an image with the superlattice reflection, I can see the antiphase boundaries which are imaged. Okay. Then another type of boundary which can come, which are called as domain boundaries, like niobium titanate. Okay, those type of structures. The C by A ratio is not 1 or multiples of lattice parameter. In such cases, because there is a slight deviation when it has to be adjusted across the boundary, okay, like here if you see that, here though this is drawn as a perfect one, okay, in actual practice in most of the lattice it can be close to 2, but not 2. So if both of them try to join together at an interface, there will be some difference which will be coming between the value. So if a beam enters here, this will be slightly shifted, so there will be a deviation which is going to come. This is going to give rise to a fringe contrast in this image. Okay. These are called as domain boundaries. Here you see that this we have taken in, you can see that the fringe contrast is being seen. So what I am trying to show you is that like stacking faults, there are so many fringe contrasts. In this particular rolla Na3b, you see that this is one fringe contrast which you see. Here you are seeing this. Which contrast belongs to which one? In fact, this belongs to the domain boundary, and in fact this contrast corresponds to stacking faults are also there. Okay. We have to do a proper analysis in this sort of systems to identify, but all of them give a fringe contrast. Domain boundaries also give a fringe contrast. Stacking fault also is present, that also gives a fringe contrast. So we have to analyze, because depending upon that, the interaction of other dislocations with them as far as plasticity is concerned, it's going to be different. The obstacle strengthening will be different for each of this type of defect. Okay. Then another is, if you have a very thin precipitate which is there, that can also bring about a phase shift in that sample. If that happens, they will also give rise to, now you see here also a fringe contrast which you see like a stacking fault. Okay. So finally when you put a sample in the microscope, you see a fringe contrast, but unless you do a detailed analysis like what I had mentioned, you will not be able to make out what is responsible for this fringe contrast. So that is why serious analysis, when you do microscopy, otherwise you will be making a lot of mistake, because one cannot think that this could be this particular type of a defect. That has to be a detailed analysis has to be carried out. I had just given that it has to be done. I had not gone into a detail to tell what analysis which is to be done. That when you start doing it, you will learn it. Okay. And another effect which can happen is that suppose you have a very fine precipitates which are there, okay, precipitates which are coherent with the matrix. Then what's going to happen is that, what is the difference between a coherent and an incoherent precipitate? Lattice, that it tries to adjust the lattice, this one. So that means that there is a strain which is going to be associated with it if the lattice parameters are not that same. Okay. Any strain is going, strain will be imaged, right, which you have considered yesterday. And if a strain is going to be there, depending upon the G vector, depending upon the value of the displacement at a particular position, that will give rise to contrast will change. So that is precisely what it is being plotted here for a microscopy which it will come, taking a theoretical calculation for a thin foil. Okay. This is what the parameter displacement which will be inside as well as outside of this one. These are all the calculations which you can see it from the book. Finally, what will happen is that this is the sort of a contrast which you see it. It is like a coffee bean type of a contrast. Yesterday, Fivel showed it. That is for a loop. Now here also you use the same type of a contrast. Okay. In fact, this is because whenever a strain field is associated which is going to be a circular dislocation or anywhere strain field is there, a similar type of a contrast will arise for both these cases. Okay. Another consequence of this sort of a contrast is that since the contrast gradually varies, this is coming from a precipitate. How do you find out the particle size? That's always going to be very different. Particle size, when you have to find out, okay, quite often we wanted to study kinetics of precipitation. You wanted to know what's the particle size traction. It's going to be extremely difficult. For that, one has to do dark field imaging with superlattice reflection, whether the precipitates are bright. Only that should be used. Okay. Yeah. In fact, this is in alloy where that, as I showed that tetragonal structure, body center tetragonal, a precipitate which is having an ellipsoidal shape. This also shows a similar type of a contrast. Looking at the image, how the contrast varies, we will not be able to make out what the particle size is. Here what we have done, it is taken superlattice reflections with which we have imaged them in dark field, and that's how particle size is determined. Okay. As Fivel mentioned yesterday, he said that the Frank loop gives rise to a fringe contrast, okay, and the contrast of these loops itself depends upon the size of the particle. Here, when the size of the loop, okay, sorry, not the particle, size of the loop. If the loop size is extremely small, okay, these are all the calculations which has been done, and it is marked here with respect to a foil where the fault is lying, okay. With respect to the foil thickness is given in terms of psi g, the extinction distance. You can see that how this contrast will be varying, it is being given. So, though it is the same type of a Frank loop, where some layer has been removed when the layer is small, like this sort of cases occur during radiation damage in many material. You can see that when the loop is small, this is like the black and white dot contrast which we call it, which you can see. This is what is which we had observed in a nickel nickel 4 molybdenum alloy which is irradiated with high energy nickel ion, we could see that. Okay. This is where some called as defect clusters, which I am not going into. Okay. In the same material, when it's irradiated at high temperature where the loop size is large, now you see the coffee bean type of a contrast. Okay. When the size of the loop becomes very large, you give a fringe contrast within the stacking fault fringe contrast you see regular, and the dislocation which is bounding it which you could see. Okay. This is a stacking fault in sink, okay, where you see that there is a line of no contrast can be. In fact, this is imaged under a condition where G dot B equals 0, okay, because the G is perpendicular to the Budget's vector of the dislocation which is in this direction, but the B cross U, because the line direction will be continuously changing for this loop, because of that the B cross U changes, okay, and for one which the B cross U becomes G dot B cross U becomes 0. Now you see that a fringe contrast like a coffee bean type you see, okay. This is a condition under which the fault is not visible, and this is a shear fault in a titanium alloy, where essentially the Budget's vector of the fault vector is in FCC we know that it is A by 2 110. Okay. When the fault vector is A by 2 110, and if the dislocation forms a complete loop, okay, then we call this as a shear loop. Okay. Here no fault will be seen anywhere because whereas if a fault which is a Frank fault which it comes, then for that the Budget's vector of this dislocation which we see will be 1 by 3 111, correct. because there is one of the layers which has been removed. So, that becomes the fault vector. When that sample is crept sample, if you look at it, the dislocations could have moved out of that slip line also. This is just an image which is being shown where you see that the dislocation line is lot of curvature is there. But to find out whether it is in a slip line or not, you have to look at that sample under different tilt conditions. That may be in the next class. When I do it, I will go into specific details and show you with some specific examples how it is being done. Okay. This is just, you take it for granted that this is at 700 degrees centigrade it has been taken. Okay. This here a glide as well as a looping has glide as well as a climb which has taken place. So, essentially what I have covered so far is talking about different types of planar faults which it has come. Okay. What are the types of contrast which it can arise, and what all precautions have to be taken, or what all conditions under which we can try to distinguish it between the different faults. Okay. Yesterday when we covered about how to characterize the dislocation, we mentioned, okay, that is like the bias vector, the line direction, as well as the slip plane, correct? And then today we have covered, if they are split into partials, okay, how to find out the fault vector, whether it is a frank partial or a Shockley partial, all those information that we have looked at it, correct? And then also yesterday we have covered about once we have characterized the dislocation, looking at the line direction and the bias vector, we can tell whether it is a screw dislocation or an edge dislocation or a mixed dislocation. Okay. All these aspects which we have covered. But one more thing which we should know to relate to plasticity is the dislocation density, correct? Okay. So, essentially I am coming back to this picture which is in thin foil. There is a particular slip plane in which dislocations are lying, and this is how the dislocations get projected. If I have to find out what the dislocation density with respect to this dislocation, what I should know, what is the volume of the sample should be known from which this image has been taken. Only when that information is there, we can find out what is going to be the dislocation density, correct? For which first what we have to do is we have to measure the distances of this dislocation and add all of them together, projected dislocations, and these are lying within this particular one. Still some error is going to be there associated with it. Okay. This I am just showing a picture which I had shown where dislocations are imaged, lot of dislocations are there. Okay. There are many softwares are there, okay, image softwares with which you can find out the total number of the dislocation density could be determined. What is essentially important is that how did we image this picture? Suppose I had imaged under a 2-beam condition, okay. We know that out of the 12 possible dislocations, depending upon the G vector which I had used, some of them are absent. That means that this does not represent the full dislocation density. Okay. For which what I have found out a method essentially is that if I go to a multi-beam condition where all the spots are equally strong, okay, I put an aperture around it here and image it around the central spot. Then since for this one 2-beam condition may be satisfied, but since the other dislocation should not be visible, since the other spot also is equally strong, it is equivalent to simultaneously taking under 2-beam condition all and trying to put them together, project them one on top of the other. So, all dislocations will now be visible. Okay. So, if we take under that condition, the total dislocation density, at least without making any assumptions, we can calculate it. Otherwise, what is going to happen is that if you have to calculate the dislocation density, you know that under this 2G condition, these are all the type of slip systems dislocations on which are absent. We will make an assumption, but we do not know how many dislocations are moving on that slip system. We will generally make an assumption that if we know that it is equally probable or not, That quite often in creep and other data I had seen that it leads to lot of errors, huge error. So if we image all the dislocations this method, then you know that all the dislocations are visible. What we have counted is we have not missed out any dislocation. So with all the errors which are there, at least we have come close to the dislocation density which is there in the material. Okay. Then we have to find out the foil thickness, correct? Because when I had shown that these dislocations which we see is from a particular thickness of the foil. So only when we divide the total length divided by the foil thickness, we get the dislocation density, the foil volume. So we know the area from the micrograph, but how do we find out the foil thickness? Okay, there are many methods which are available. Okay, one of the method which is used is using convergent beam electron diffraction. Any of you have studied convergent beam electron diffraction? Okay, normally whenever we do a diffraction, okay, what do we essentially do? Make the beam parallel, okay, so that a diffraction is taking place. Instead of taking a beam parallel, if I converge the beam, what will happen? That means that it is essentially having a beam converged like this, falling onto a sample. That means that I can assume this to be equal to so many directions which are there within this range of angle. So beam parallel to each other with various orientations which is falling onto that sample. Some particular orientation will exactly satisfy, others we can put that S is varying, deviation is varying. That is precisely what it happens in this case. What is the variation in S when it happens? We saw that in a foil which is wedge shaped, if the thickness varies, right, S remains constant, then that gives rise to a fringe contrast. Similarly, if the thickness remains the same, S varies also, a similar effect should happen. That is precisely what happens in the convergent beam diffraction.